welcome to BMD lecture series. This is Rudra Pradhan here, and today we will continue with predictive analytics, and that too again coverage on linear programming problem. We have already discussed couple of problems, and we have also highlighted different kind of situations and different kind of business problems through which you are looking for the optimum solution with simple kind of structure, complex kind of structure, various issues, and several complexity. Still we are actually having a kind of optimum solution as per the business requirement or the kind of management requirement. And in fact, till now whatever problems we have discussed, and we are looking for the kind of solution by applying a typical structure called as graphical structure. And in this kind of environment, there may be a kind of situation where more number of decision variables may be operative, and again with respect to objective function and constants, we are looking for the optimum solution as per the business requirement or the kind of management requirement. Now, when a problem is complicated with respect to more number of decision variables and more number of constants, and then the graphical methods may not be very effective to come to a kind of solution. In that context, analytics has a kind of big rules, either through a kind of computer programming and or through a kind of some typical softwares through which you can solve the problems more effectively as per the management requirement and the business needs. And in fact, without any softwares or the kind of programming, still we can solve the problems as per the particular business requirement, and the solutions which we will like to address here today is the kind of simplex procedure, and this is otherwise called as simplex methods or algebraic method, through which we look for the optimum solutions corresponding to a particular objective function and the constants, where we typically use this particular mechanisms with respect to more number of decision variables in the systems. And let us start with the particular structure, and after highlighting the particular simplex structure, then we will solve some of the problems by the kind of software use. Maybe solver we can use here to solve this kind of problem, and this is a very interesting technique. We have lots of advantages to solve some of the problems corresponding to constants and the kind of consistent and the kind of conditions. So, what is happening here in this algebraic method and the kind of simplex method, it is basically a iterative kind of environment, and the procedure is to move one kind of iteration to another kind of iteration, and then we will continue till we get the optimum solution which can satisfy all the constants, the conditions, and the kind of objective function requirement. And that means typically it is a kind of method of improvement. So, one iteration to another iteration, like it is a kind of chain, and the beauty of this particular mechanism or the kind of structure is in each stage. So, means each subsequent stage we will find improvement in the objective function subject to the kind of constant. Then finally, you reach the optimality, where the value of the particular objective function can reach the highest level with respect to a maximization type or minimization type. After that, you may not get the anything best corresponding to the objective function and constant. So, that is how this is a very standard kind of structure, and most of the big problems and big kind of management kind of scenario, where algebraic method will be very useful to look for the very useful to use and then look for the kind of solutions. So, linear programming models have a fewer equation than variables. Unless number of equation equals the number of variables, a unique solution cannot be found. This is like means altogether it is a kind of simultaneous equation systems where we have more number of decision variables with respect to constants. So, that means in a kind of simultaneous equation system setup where if the constants are not consistent with number of variables, then we may not get a kind of unique solution, and that is also equally applicable in this process of simplex methods, and as a result we may not get optimum solution. So, now some of the notation we like to know, then accordingly we can look for the kind of solution. Typically any linear programming problems. So, we like to optimize z equal to c x and x less than equal to or greater than equal to b, x greater than equal to 0, but here a is nothing but actually the aij coefficient. So, that is actually input to the decision variables, and b is the kind of vector which is actually a the kind of balance or the kind of restrictions towards the particular constant, and then c is the coefficient of vector involving the weights or coefficient to the decision variables. So, accordingly the typical understanding is the c j coefficient, that is the objective function coefficients, a I j is the coefficient of the variable corresponding to constraints, and that to left hand side of the model, and then b I is the right side of the constant, and that to reflecting the vectors which represents b 1, b 2, and depending upon the number of constants in a particular problem. So, now knowing all these things, so we can move to understand the particular requirement, and then moving forwards we will have a problem like this. This is a kind of structures, and the kind of structure is like this to understand the particular requirement, and okay. Okay. So, this is what the typical problem, and corresponding to this problem. So, this is actually first hand problems where we have objective function corresponding to variables, and that to maximizing z equal to 60 x 1 plus 50 x 2, and subject to we have a constants for x 1 plus 10 x 2 less than equal to 10, 2 x 1 plus x 2 less than equal to 22, and 3 x 1 plus 3 x 2 less than 39. We have already solved this problem, and here the first and issue is to make the constant into equality. That means, we try to put in a kind of simultaneous equation system where all the equations must be in a equality format, and in reality this kind of problem. So, we may have a less than constant, we may have a greater than type of constant, but the first and requirement to apply the particular methods, that is a simplex method, is to make the constant into equality. After using or introducing slack and surplus variable, and that means there are two different structure we have to follow to make the constant inequality constant to equality constant, and that is the first and requirement of any kind of simplex mechanism. And when a particular constant is less than type, then the variable which can use to transfer the less than type to equality is called as slack variable, and when a constant is greater than type, to make the you introduce new variables through which that less than type constant, that is the inequality type of constants, can be moved to equality constant, and in that case the particular adjustment is through a variable called as surplus variables. That means, when a constant is less than type, we introduce slack variable to make the constant into equality, and when a constant is greater than type, we use surplus variable to make the inequality constant into equality constants. As a result, S 1 is the kind of since all are less than type. So, now S 1, S 2, S 3 3 different slack variable is used for 3 different constants, and that to make the inequality constant into equality constants. And actually the simplex procedure follows directly a kind of mechanism called as a matrix structure, that is the Gauss elimination procedure, and here the particular mechanism is we have a original input matrix, and then we have to create a kind of identity matrix, unit matrix, depending upon the actual requirement of the kind of constants. For instance, here there are 3 constants, and as a result we need a kind of unit matrix of order 3. As a result, S1, S2, S3 can give you 3 different unit matrix structure. So, x1 where the first component will be the unit matrix, the S2 the second component will be the unit matrix, and S3 that is the third component of the unit matrix. That means, technically the typical structure will be S1, S2 and S3. So, this the structure which we can follow is like this 1 0 0 0 1 0 and 0 0 1, and that is what the all the diagonal elements will be uniquely established. And then since there are 3 constants, so 3 in variables slack variable is used to have a unit matrix of order 3. As a result, we apply the inverse structure through which the first and input matrix will convert into the unit matrix. As a result, we can able to reach the optimum solution, and accordingly we look for the solution and the kind of management requirement. So, accordingly the symbolizing format is like this. So, it is a C1, X1, C2, X2, and these are all artificially introduced variables. So, since it is artificially introduced variable to make the constant into equality, so as a result the objective function coefficients of the objective functions will not available, and since it is not available by default, the coefficients will be means we can introduce 0 coefficient here by default, and then we look for the kind of solution. So, the procedure of solution is like this, and so the typical procedure is we like to prepare a matrix like this, and here. So, these are the initial input matrix, and this is how the unit matrix, and in totals if you simplify further, then this is what the actual matrix and this is what the unit matrix. So, now we will introduce in such a way that so this variable will be transferred into a unit matrix format. So, as a result, so the particular variables optimality can be reached. So, that means, the usual structure is this could be the unit matrix, and by default this will be going through a kind of inverse matrix of original matrix. So, as a result it is a kind of iterative procedure, and we will move one step to another steps, and accordingly every stage we will get the improved objective function value, and then finally you reach the optimality where the particular transformation will be unit matrix, and then the original matrix will be going through a kind of inverse matrix structure, and by default we will get the optimality and the kind of the solutions as per the particular business requirement. So, accordingly, so the procedure is so to set prepare the format like this. So, these are all the right hand constant of the particular structure, and these are all left hand side of the constant, these are the right hand side of the constant, and these are the kind of newly introduced artificial not exactly the artificial structure, but it is the kind of slack variable structure through which actually we look for the kind of optimum solution. And then the the procedure to move is like this, and this is what the kind of structure. So, what will you after introducing all these things, so that means this is the original input structure, and then so this is the after the introduction of the slack variable, and then finally it is the kind of first and optimum solutions, but it is not the final optimum solution, because we have not reached the optimality as per the constraints are the condition is means conditions are constant. So, typically the procedure is here. We have a concept called as net evaluations, and that is the difference between the cost coefficient and the z value, that is the objective functions, and then we like to know what is the procedure through which you can get the optimum solution. So, that means, typically the idea is that it is a kind of basic matrix through which you can get the values of the decision variables. So, in the basis matrix it should be in a kind of unit matrix format. So, that means in a, if it is not exactly the particular requirement. So, what will you do? We like to move do the kind of movement. So, the kind of incoming structure and outgoing structure. So, that means initially in this particular format S1, S2, S3 are the kind of first hand entry, but actually S1, S2, S3 is not the original values of the decision variable. As a result, this cannot be the final solution. So, then what should be the final solution? So, that means the final solutions either x1 will be there no x2 or x2 will be there no x1s, or both x1 and x2 can be there. So, as a result, so the the kind of processing is x1 can be entered either in the place of S1 or in the place of S2 or in the place of S3, or the move will be x2 can be the incoming vector and the outgoing vector will be S1, S2, S3. So, that means x2 can be in the place of either S1 or S2 or S3. So, likewise, so that means this will be go like this, or this will be go like this, or this will be go like this, and again. So, this may be the first move, or if not the first move, then x1 can be the first move. So, x1 can be replaced to S1, x1 can be go to x2, or x1 can be go to the x3. So, that means we have several kind of alternative structures, but which one will be the first hand priority and then move go on and to reach the final optimum solution. So, there is a procedure, and in the procedure of simplex method. So, it depends upon which particular, obviously this cannot be the final optimum solution. So, either x1 will go and S1, S2, S3 will be out, and then x2 will go again S1, S2, S3 will be out, then finally we look for the optimum solution. So, it depends upon the net evaluation, that is the C minus z, and that is the objective values of cost coefficient of the objective function, and the z structures, the kind of net evaluations, and on the basis of that we can actually take a decisions. So, usually we will stop where where all the net evaluation will be negative, or it is actually 0 with respect to unit matrix. So, if not, then we will continue. So, now in the first end these are all, this is coming positive and this is coming 0. So, this is okay. So, for optimality this is final, means fine, and in the case of x1 and x2. So, this is coming actually positive. So, that means we have not reached the optimality. So, we will reach the optimality when the for any unit matrix. So, the net evaluation should be 0, and for other vectors. So, the net evaluation should be negative, since x1 and x2 which is not which are not actually the unit matrix. So, by default this could be the incoming vector through which you can move, and finally, we reach the kind of optimum solution where both the vectors, these are all called as a non basic variables right now. So, they will be coming into the basis matrix, and finally, they will be the basic variables, and again as usual structure is this could be the negative signs. So, then we can reach the final optimum solutions, and accordingly moving forwards. So, by applying these rules, so we can move again to this particular process, and this is how the coming to the in the first hand choice corresponding to the previous kind of situation. So, now we have actually calculated the net evaluation, and that means technically x1 can go or x2 can go in place of S1, S2, S3. So, in that case what will you do? So, the procedure is the highest or largest positive value could be the first hand priority. So, as a result with this values, so 60 is the highest one, and that is against actually x1. So, that means technically the indication is that x1 is the incoming vector either in place of S1 or S2 or S3, and if x1 is going in place of S1 or S2, S3, then by default S1 S2, S3 will be the leaving vector. So, now with this particular indications, x1 is the incoming vector, then which one is the outgoing vector out of S1 and S2, S3. So, we have to take another kind of indication, In that case, the indication is the kind of minimum ratio between x b and by x k. So, x b is the right hand side of the constraints, and the x k is the particular particular vector which can be the incoming one. So, as a result, so the minimum ratio will be 100 by 4, 22 by 2 and 39 by 3 corresponding to the particular structure. So, as a result, this will be the combination. So, we like to find out the minimum of 100 by 4, then 22 by 2 and then 39 by 3. So, we if you simplify, then you will have a 25, 11 and 13, and as a result 11 is actually the minimum one. So, by default, so this will be the indications. So, as a result, so this is the indication that the second vector is the outgoing vector corresponding to x 1. So, x 1 is the incoming vector, and then this particular indication is the S 2. So, that means x 1 will go to S 2 and S 2 will be coming this place. So, the accordingly the movement will be like this, and the kind of intersection is called as pivot element. So, that means in this will be now unit matrix, where the position of unit will be the middle one and the remaining place will be 0 0. So, as a result, so the particular S 2 this is the S 2 format actually. Now, this S 2 format will be moved to this place, where x 2 will be the x 2 will be coming here and the S 2 will be coming here. So, as a result, the particular transformation will be in a different structure altogether. And now, in order to understand again, so how is the kind of improvement. So, you can go to the next tables, and then the next, this is how the graphically you can also cross check, and again, so the particular structure is here, and this is how the kind of structure, this is how the pivot element corresponding to the entry. So, that means the x 1 will be coming here and S 2 will be coming here. So, accordingly we can actually move forward, and then finally we look for the kind of solution. And in the second iterations, this is how the now the kind of x 1 is coming here as usual the indications, and x 1 is coming here, and then the kind of S 2 will be now change the kind of position. So, obviously, so the new improved solution will be the indication is like this, here x 1 is coming in the place of S 2. So, as a result, so now x 1 will have actually unit matrix, because it is coming in the basis matrix, and the particular S 2 is coming here in the case of x 1. So, now this is the kind of optimum solution after the first iteration. And if you compare here, the z value is actually having improvement, and compared to the previous one. In the previous one, the z value is simply 0, because these are all the coefficient of z value. So, now here actually corresponding to objective function, so 60 with respect to x 1, then obviously z is having positive value. So, now by the way, whether means before we calculate the optimality of z, we like to check whether we have reached the optimum solution as per the simplex guideline. The simplex guideline is that we will reach the optimum solution when the values of the means the net evaluation for unit matrix will be 0, and the particular non-unit matrix, the net evaluation will be the negative ones. So, now for that we have to first check the net evaluation, and then we think about the optimum value of z. If not, then we will move, or we will move to this second iteration and then look for the kind of solution. Now, after the first iteration, the final table or final structure will be like this, and this is how x 1 is entering in place of S 2, and as a result x 1 is now unit matrix, and again we calculate the net evaluations. By default, since x 1 is unit matrix, net evaluation will be 0, and this is coming negative, and this is fine. and this is 0, this is fine, this is also fine for optimum solution, but this is not fine because this has a positive value for x 2. That means technically now highest positive value will be the kind of new incoming vector, and as a result here x 2 is the only variable, only vector through which it can enter to the next iteration. So, that means now x 1 has already coming to the kind of basic matrix or the kind of optimum structure, and now x 2 is also having indication to come to the basic matrix for the optimum solution. Now, like the previous case, so x 2 is the indication of incoming vector. Now, we are looking for which place x 2 will move, either it will go to the s 1s or it will go to the x 1 or it will go to the s 3. Since x 1 is already replaced with s 2. So, there is a less chance that x 2 will go to x 1s. It may be possibility is there, but there is a high chance that now x 2 may be replaced with s 1 or s 3. So, let us see how it can be actually having the kind of final solution. So, now with the particular results, so it is the indication that x 2 will be the incoming vector. Now, we are looking for outgoing vector through which you can do the kind of interchange x 2 with either s 1 or x 1 or s 3. So, now for that we again go to the minimum ratio, that is the x b by x k. So, which is nothing but actually the right hand side of the constant with respect to the input to the kind of second vectors, that is x 2. So, as a result, so we can get a clue that which one is the minimum ratio, and the kind of vector which is having minimum ratio, by default that will be the outgoing case. So, as a result to know the reality, so we can move to the result part, and here the if you simplify the minimum ratio, which is actually here 56 11 and then 6, and against the income input x k, that is the input of x 2 is 8 1 by 2 1 by 2. So, now if you simplify here this particular structure, so you can get to know the minimum ratio. So, out of these 3, so the minimum ratio is the 4, and as a result, so by default this will be the outgoing case. So, that means technically, so this is the incoming indications because it has a highest positive net evaluation, and here is the minimum ratio. So, as a result the final decision is the s 3 will be the outgoing vector and x 2 is the incoming vector. So, that means technically, so the substitute will be like this, x 2 will be coming to s 3 and s 3 will go to the x 2. So, then while doing this we will again get the improved optimum solutions, that is called as improved basic feasible solution, and then again we check the kind of requirement. If the particular requirement is satisfied, then that could be the final optimum solution. If not, then again we move on till we get the further improved optimum solutions, and corresponding to this. So, it is clear cut indication that now the x 2 will be replaced, and that 2 in place of s 3, and s 3 will go in place of x 2. So, that means now in the basis matrix in the second iterations it will be x 1, x 2 and s 1s. So, then accordingly we move forward, and this is how graphical again indication. So, again we are looking for the kind of solution, and here by default x 2 is coming to the coming in place of s 2 and again s 3. So, again this x 2 place will be the unit matrix, since the third row is the kind of interchange. So, by default the unit matrix position will be the 1 here, and as a result, so this is 0 1 0 already, and this will be 0 0 1, and in fact s 1 is now changed corresponding to the first iteration and second iteration. So, as it is s 1 will be there. So, typically now basis matrix s 1, then x 1, then x 2, and by default s 2 and s 3 is already replaced with x 1 and x 2. So, now this could be the final optimum solutions, and the declaration is declaration is on the basis of the check of net evaluation, and accordingly we will move to know the kind of net evaluation value through which you can take the decision whether we have reached the optimality or not. So, now after the second iterations, this is the final outcome. So, now x 1 is already replaced with the S 2 and x 2 is already replaced with the x 2 as a result. So, this is now in the basis matrix and it is good for the optimum solutions as per the particular business requirement, and in fact, S 1 is still in the basis matrix, but there is no way now out. If it will be out, then obviously either S 2 or S 3 will be in the process, because we need actually 3 matrix basis matrix through which actually you can streamline the process depending upon the kind of constraints. And now now to declare the optimality or the final solutions, we have to check the net evaluations, and again for that we have to calculate the net evaluation, and again by default net evaluation will be 0 for the unit matrix, that is satisfied. This is also 0, that is satisfied, and this is also 0, that is satisfied, and again net evaluation for non basic variable which is not a unit matrix, then it is coming negative -10 for S 2, and it is again -40/3, it is again for S 3. So, that means the rule is that once the net evaluation will be 0 or either 0 or negative, that means we have reached the optimality. So, technically in this means for these problems we have reached now the optimum solutions as per the simplex requirement is concerned. So, the kind of net evaluation value is coming 0 for unit matrix, and for non unit matrix it is coming actually negative. So, that means this is a clear cut signal that we have already reached the optimum solution. Then in the optimum solution, the combination is S 1 and x 1 and x 2, and then the cost coefficient is actually coming 0 for S 1s by default, and x 1 is this is 0, then 60, and this is 50. Okay. So, now we have reached the optimum solution. Now, we like to know what should be the optimum kind of structure. So, that is the cost coefficient, and again so far as the values of the decision variable is concerned, this is what the x b, that is the values of the basic variables. So, now corresponding this is actually coefficients of the objective functions, and the corresponding values of the decision variable will be for S 1 it is 24, and then for x 1 it is 9, and then for x 2 it is actually 4. Now, in the objective functions our representation is with respect to x 1 and x 2. So, as a result C 1 x 1 plus C 2 x 2, that is the linear combination between x 1 and x 2. So, now C 1 is nothing but actually 60, which is already given in the initial problem formulation, and 50 is also C 2. So, now with the operations we get the optimum values of the decision variable, that too for x 1 it is 9 and for x 2 it is actually 4. So, as a result the final z value will be 9 into 60, so, and plus 4 into 50. So, that means technically 60 into 90 plus 50 into 9, that is C 1 x 1 plus x 2, which is actually coming the value called as 740. In fact, this particular problem we have solved through graphical method already, and we have already got the similar kind of results. Now, simplex method is also giving the similar kind of results. That means this is somehow verified, and the in fact the algebraic method and simplex method is much better technique than the graphical structure, where we can actually have a flexible kind of scenario. That means in the graphical structures the first hand requirement is to find out all such corner points where the optimum solution can be having, and then we actually check which one is the final optimum solution. But the beauty of this particular simplex structure is it is a iterative process, and each iterations will have a kind of improved feasible solution. That means, this similar kind of corner points are also here, but all the corner points corresponding to the z value, it will be appearing like ascending to descending. So, that means, the minimum z value will be at the origins, where particularly for this problem with respect to x 1 and x 2. So, if you arrange the values of the decision, means values of the objective functions corresponding to x 1 and x 2. So, the minimum minimum value of z is where x 1 equal to 0 and x 2 equal to 0, as a result z equal to 0, and then any improvement of either x 1 or x 2 or both, then slowly the value of objective function will move forwards, and finally will stop at a particular point where the value of the objective function reach at the highest level, and then other condition also satisfied, and then we freeze the solution as per the particular business requirement and the kind of management requirement. So, so technically, so we have now reached the optimum solution, and as a result the values of the decision variable here x 1 equal to 9 and x 2 equal to 4 and s 1 is 24, but actually s 1 is not the variable in the original setup. So, as a result the final optimum solution is with respect to x 1 and x 2, and objective function is already there. So, just you put the value and get the kind of value of the objective function, which is actually coming 740, and that means technically z optimum is 740 subject to x 1 equal to 9 and x 2 equal to 4, and that is the typical optimum solution corresponding to this problem. And then if any kind of change situation is there, so we have to move accordingly as per the particular requirement. So, now to sum up all the kind of discussion. So, the summation is that algebraic method or simplex method is a kind of structure where predictive analytics can solve, prescriptive analytics can solve some of the problems, business problems depending upon the particular objective function structure and the kind of constraint where we are looking for the solution as per the typical business requirement and the kind of management requirement. Compared to graphical structure, simplex method is a very standard structure and very systematic and very effective, as the movement from one stage to another stage, in each stage of movement. So, the values of the objective function has a kind of increasing structures, that is with respect to maximization, and even if in the kind of minimization, the particular structure will be also follow as per the particular structuring is concerned or the kind of requirement is concerned. So, in total this is very effective tool to solve some of the business problems as per the particular prescriptive analytics environment is concerned. So, so these are all kind of structuring. So, how we have to reach all the kind of solution as per the particular business need or particular business requirement. And in fact, like the previous discussion, we have normal case and we have actually complex case, where in the normal case corresponding to objective function, the constants means if it is maximization, the normal case is the constant should be less than type, and if it is minimization objective function, then the constant will be greater than type. But we have solved some of the problems where the constants are mixture type, where greater than, less than, and again there are certain like this case here, and in totals again we may have a kind of situation where some constraints are conflicting, and some kind of structure like multiple solutions, unbounded solutions, infeasible solutions. So, again in the algebraic methods, the kind of indications starting with infeasible to unbounded, then up multiple. So, it will be more interesting kind of structuring through which you can actually explore through simplex method, and then take the decision about the particular business problems, and the kind of management requirement. and then accordingly we will have a solutions as per the particular business requirement. And in fact, if it is a maximization type a situation, then it is very easy to solve simplex method as usual procedure. But when we have a minimization problem where some of the constants are greater than type or equal type, then depending upon the particular constant number of constants, so we need to have a unit matrix format, but by default we may not get a kind of unit matrix format. That means technically the problem which we have solved earlier, it is the less than type situations where there are 3 constants, and introducing slack variables we can easily get 3 unit matrix as per the simplex requirement is concerned. But this is a kind of problem where less than type, equality type and greater than type, but after introducing slack and surplus wherever there is a requirement, so we may not in a position to get actually 3 unit matrix as per the particular requirement. So, that means technically in this kind of situation we have a simplex method with a different kind of mechanisms to look for the optimum solution, and there are 2 different methods again under the simplex method, and that to a situation where we have a constant constant like greater than type and equality type, that is called as method 1 BGAM, and the alternative method is called as 2 phase mechanisms. In the BGAM methods, so we like to introduce additional artificial variables which is represented as unit matrix as per the number of unit matrix is concerned. So, that means technically after introducing slack variable, then you like to check actually how many unit matrix are lacking corresponding to number of constant available in a particular model. So, for example, if there are 3 constant in a particular model and we have a one kind of unit matrix by introducing slack and surplus variable, then by default we need 2 more kind of unit matrix to start the process and to look for the optimum solution. In that context, we introduce 2 artificial variables, and which is actually kind of unit matrix format. For example, so this is what the kind of case here. So, we introduce 2 artificial variables with 2 unit matrix, because the original problem is up to this much where we have only 1 unit matrix, and that too we have actually 3 different constants. So, as a result simplex method will not work, and in this context, so we have to introduce 2 artificial variable to start the process. And so far as a BGAM mechanism is concerned, so the cost coefficient to BGAM mechanism is we can start with introducing minus m, and then as usual you can proceed like this, then final optimum solution we can reach where the net evaluation will be 0 for unit matrix, and for non unit matrix it should be having actually a negative kind of situations, and that too with respect to adjustment of m is a kind of positive number here. So, then finally you will reach the optimum solution. And in the case of 2 phase mechanism, so we start with a similar kind of structure, but in the phase 1 we introduce artificial variable number of artificial variable as per the unit matrix requirement, and then apply cost coefficient kind of unit minus 1, then again you solve. Once phase 1 will end, and then we start with the phase 2 where the actual cost coefficient will be there, and we can remove artificial variables and then look for the solution, and the final solution will be again judged on the basis of net evaluation criteria, and or by default you will get the optimum solution as per the particular business requirement and the kind of management requirement. So, looking forward actually, so these problems you can actually move, and then finally we can see the kind of solution here. So, this is how the similar kind of this is how the largest positive value, and by default this could be the incoming vector indications, and then we by the kind of minimization criteria we look to find out which one is the outgoing. So, in the case of earlier problems, we like to actually it means our target is to remove all these slack and surplus variable in the basis matrix and bring the actual decision variable to the basis matrix, that is the kind of optimality or optimum solution. But here we have a challenge again. So, it is not the removal of slack and surplus from the basis matrix, it is the target is to remove first the artificial variable from the basis matrix, and then try to bring all the decision variables to the basis matrix as per the particular requirement and the particular business problem is concerned. So, likewise if you move forwards, then simple structure you will look for the optimality, then finally we will reach the optimality and then look for the optimum solution. So, that means corresponding to this particular problem. So, here now we have reached the optimum solutions, because here the for unit matrix we have actually net evaluation 0, net evaluation 0, and again for non unit matrix. So, we have actually net evaluation negative, that means we have reached the optimality, and in the basis matrix x 1 is a one kind of an entry and x 2 is the another kind of entry, and no artificial variable. In fact, the slack and surplus variable is there, that is S 3, and as a result, so x 2 is equal to 4 here and x 1 is 5 here, and corresponding objective function coefficient is 8 and 6. As a result, see the value of the objective function will be 8 into 4 plus 6 into 5, and that is coming actually 62, and we satisfy all the condition and constant, and then finally, this is the optimum solution corresponding to this the particular LP model is concerned. So, likewise we have a different kind of structure through which you actually you can look the kind of solution, and to verify this one, since it is a two variable case, you can also verify the case with respect to graphical and look for the solution. And this is another kind of problem through which actually simplex method can be applied and look for the kind of solution as per the business requirement. So, that means technically we have actually different kind of structure, different kind of setups, different kind of conditions through which actually the actual business problem will be fitted, and then we look for the optimum solution as per the business requirement, subject to satisfying all the conditions and the kind of constant, and whatever may be the shape of problems, whatever may be the constant and conditions, the prescriptive analytics is a very helpful kind of structure through which you can have a solution which can solve the business problem as per the particular management requirement is concerned, and then we will in a position to take or to go for effective management decision. With this we will stop here. Thank you very much. Have a nice day.